Well, my most important approximation technique. This is what I'm going to concentrate on. I'm sorry it's so light on the last video, but I'm going to leave that for you. It's an online course, so a bit of independent study. Take a peek at the left endpoint rule, right endpoint rule, midpoint rule, trapezoidal rule. As far as testing you, I'm going to focus on Simpson's rule. So can you allow me just a few moments to talk about this theoretically? Here's what Simpson's rule does, and here's where it's so unique. Okay, I need to be mindful of the colors, what's going to show up. I'll start off with blue. So, Simpson's rule only applies if you have an even number of subdivisions for this reason. I'm going to take 3 of these ticks at a time, go straight up to the curve, look at the corresponding points in the curve. I'm sure you learned from pre-calculus that 3 points uniquely determine a parabola. So to approximate the area of this curve from A to B, that is to say, to approximate this definite interval, I am at least over the 3 first ticks, or the first 2 subintervals, construct the unique parabola past those 3 points. And I will compute the area underneath those 3 parabolas. I think the area underneath the parabola is going to approximate, usually fairly well, the area underneath the black curve over the first 2 subintervals. Sorry, Pythagoras' tail is getting a little crazy. Over the next 3 subintervals, I think I misspoke. Over the next 2 subintervals, with these 1, 2, 3 ticks, I'll go straight up the curve, look at the 3 points on the curve that have those 3 x coordinates, and look at the unique parabola past those 3 points, and compute the area underneath that parabola to approximate the area underneath the curve over those next 2 subintervals. And I'll repeat the process until I get to the last subinterval. Now, notice how this point was used twice in the computation of the area underneath the blue parabola and the red parabola. So keep that in mind when I put this all together. You really could ignore this video if you want, because this is theoretical. So I'm just explaining what Simpson's rule is all about, why Simpson's rule is what it is. All right, next on my list. I don't like my picture, so if you don't mind, can I take the entire graph and shift it to the left, x sub 1 units, so that when I shift this to the left, the first 2 intervals are straddled over the origin symmetrically. I think he fell asleep for safe. So here's x sub 0, here's x sub 1, here's x sub 2. And if you don't mind just rephrasing them or renaming them because it's going to be convenient for me, how about negative h? This is 0 in h. So for me to compute the area underneath the parabola determined by these 3 points here, here, and here, I'll try to draw it in. It's not exactly equal to the curve over that interval from negative h to h, but approximates it. And I'm going to come up with the area underneath that blue parabola and use it to approximate the area underneath the curve, at least over the first 2 subintervals. So here we go. I think the area underneath the parabola is a definite interval evaluated from here to here of my quadratic function. Now, y equals f of x is black, but the blue curve is a parabola. It's got an equation of this form. So I'm looking at the area underneath this quadratic curve to approximate the area underneath the graph of y equals f of x, at least over the interval from negative h to h. So, in anti-differentiating, now taking this antiderivative, evaluating both at the upper and lower bounds of integration, then subtracting. Now, clearly, these 2 terms, where are they? Here and here cancel. And I think that's going to leave me with this. And if you allow me to come in and maybe pull out a factor of maybe a dh over 3, here's what's left over. I'm getting nervous. I'm worried I'm running out of room. So because I'm kind of worried about the room, can I just take a really quick break? Pulling out a nifty piece of scratch paper, making sure I'm not getting too small. Let me go take that quadratic function, and let me take that quadratic function and evaluate it here, evaluate it here, and evaluate it here. So in case I'm not being very clear, y is nothing more than that quadratic beast you see in blue. Now at h, I think you get this. At 0, I think you're getting this. At negative h, I think you're getting this. Now, if you're okay with that, let me massage what I have here. Because I think this is h over 3 times my 2ah squared, which can be interpreted as ah squared plus ah squared. Now, the 6c can be interpreted as a plus c. Well, can I add to that? I'm trying to save room, it's not working. Let me slip in real quick. I'm not changing anything. Just give myself more room. Now, notice how I can add a BH here, but if I subtract it here, it doesn't make any difference. I'm just adding a funky looking form of 0. Oh, you know what? I think I messed up. Watch. The arithmetic doesn't match up. AH squared plus AH squared is here. C plus C is here. These two cancel. But this C plus C is just 2C, not 6C, so I better add in 4C to compensate. That being the case, wow, I think I might make it with my board space. That H is nothing more than delta X. Technically speaking, that is nothing more than f of h. I'll put it at the end. This is nothing more than f negative h. And if you look carefully enough, that 4c can be interpreted as my function f. I called it f, I should say y. My goodness. I'll be consistent. I'm just looking over there realizing I need y instead of f. That 4c can be interpreted as y0 times my 4. All right, everybody, look at what I have. The area underneath the first two subintervals, that is to say, under the graph of this equation in black, can be approximated by the area underneath that blue parabola, which is computed by looking at that parabola evaluated the left endpoint of the first subinterval, plus 4 times the left endpoint of the second subinterval, plus 1 times the right endpoint of the second subinterval. So when I shift back x sub 1 units to the right, approximating this definite interval with Simpson's rule using n subdivisions is going to be obtained by looking at delta x over 3 times f evaluated negative h. Well, I shifted back x sub units, so now that negative h becomes x sub naught, plus 4 times f evaluated x sub 1, plus f evaluated x sub 2. But now when I add the area underneath the second red parabola, I get that f evaluated x sub 2 again, so my coefficient out front is a 2, plus 4 f evaluated x sub 3, plus 2 times f evaluated x sub 4, plus dot, 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 all the way down to a 4 times f evaluated x sub, sorry, I misspoke. How about 2 times f evaluated x sub n minus 2, plus 4 times f evaluated x sub n minus 1, plus lastly, a single f evaluated x sub n. And there is what I use as an approximation technique to approximate this definite interval. using Simpson's rule with n subdivisions. Now I'll provide you with some examples.